Okay, I want to walk through a problem that's a little bit trickier than some of the ones that we've seen before. So if you've seen some of the other videos, we've played around with some titration calculations. But this one's a little more challenging because we're looking at a system with a weak acid, a strong base. And so if you've seen the video on titration curves, you kind of know what that looks like. This is saying I'm reacting this to the equivalence point, and I have this amount of my acid, and this is my concentration, and I'm titrating with this concentration of sodium hydroxide. So there's a couple things that I need to know here. First of all, is this says that it's at its equivalence point. So at the equivalence point, which I'm just going to abbreviate there, what that means is that I've reacted as much hydrogen as I possibly can with my hydroxide, that these concentrations are equal to each other. Now, if these are equal to each other, the amount of hydrogen is equal to the amount of hydroxide, then that would mean that I have a pH of 7. But that would be under perfect conditions where I have nothing else in the solution. If I have as much hydrogen as I have hydroxide, then it'd be right in the middle of my pH scale. But if I have a salt in solution that has the potential to give ions that are going to hydrolyze the water, then that's going to have the potential to mess with the pH of my solution. So if you've seen some of the former videos, then you know that sodium is coming from sodium hydroxide, so it's not going to hydrolyze water. But the fluoride ion, because it's coming from hydrofluoric acid, and even though hydrofluoric acid is a scary acid, it's still a weak acid. When fluoride reacts with water, it hydrolyzes it, forming or reforming hydrofluoric acid, and then my hydroxide ion. So this hydroxide ion and how much fluoride I have in solution, this little side reaction here is going to cause all of the change in pH. Any difference in the change of the pH from 7 is going to be caused by this side reaction. So this is really what I care about in all of this. So what I need to do is figure out how much of this I have in solution when I react these together. And then I can use that concentration of my fluoride in an icebox to find this guy. Okay, so this is kind of what I affectionately call a hold my beer problem, right? So I'm giving you all of this information. We know that story problems are notoriously challenging to kind of unpack and figure out the information that we're given and what we're looking for. But hold my beer, I can solve this thing. So what I need to find first is the concentration of my fluoride. And to do that, I need to figure out how many moles of fluoride I have and how much total solution I have. So we can do that in kind of either order, but let's figure out first the amount of sodium hydroxide I'm using, because that's one piece that I'm missing. I'm given a volume of my hydrofluoric. I need to know the volume of my sodium hydroxide to give me my total volume of solution, because what I need for this guy is the number of moles, and I need to know the total volume. So this kind of gives me a little checklist of what I need to figure out in order to solve this dang problem. Okay, so let's take what we know about our hydrofluoric. This is just going to look like any other titration type problem. I'm going to do this conversion just right off to simplify my math. You guys are snappy with metric conversions at this point. So my 25 milliliters of hydrofluoric acid, this is an L, is 0.025 liters of hydrofluoric. I'm given a concentration that gives me moles, so I need to figure out what my molar ratio is between my two. It's a monoprotic acid with a base that just has one hydroxide to give, so it's going to be a 1-to-1 ratio. And then I know my concentration of my sodium hydroxide because that is given. Okay, so my setup here is going to give me the number of liters, and I end up with this many. And I'm keeping an extra sig fig here. We'll round at the end. So I have 0.0166 16.7, so that'd be 16.7 milliliters if we're thinking about it in those terms. So in order to get that total volume, I need to add that number of liters with my number of liters of hydrofluoric. And then I'll round here to my 2 sig figs. All right, so my total amount of solution is, 42 milliliters. So that gives me this, because I'm still trying to find the concentration of my fluoride ion. Okay, so I have the total volume. Now I need to figure out the number of moles that I have of that fluoride. So how am I going to do that? Well, I need to go back to my volume of hydrofluoric, because that's where they're coming from. And I can go to my concentration to find my total number of moles of hydrofluoric. So this kind of looks the same in terms of setup. But this one I'm not looking for moles, or I'm not looking for liters, right? I'm looking for moles ultimately of my fluoride. So I'm going to have to use my balanced chemical equation and some of these molar ratios to get there. So in every 1 mole of hydrofluoric, I'm going to form 1 mole of sodium fluoride. Okay, because what we're ultimately looking for is the fluoride that's in solution here that's free at the end, and that's going to be in this compound which is soluble in the solution. And now for my fluoride, in every 1 mole of that sodium fluoride, I get 1 mole of the fluoride ion. And you may be able to look at this equation and just say, well, this is 1 to 1, this is 1 to 1, this is 1 to 1, so all these conversions could kind of work themselves out. But it's good practice with dimensional analysis to make sure that we're getting an answer in units that we're looking for. In this case, again, we're looking for the number of moles of fluoride. So when I plug and chug through that, I get this, 2.5 times 10 to the negative third moles of fluoride. And we're looking at, the 2 sig figs along the way. So that's this part. All right. So now I have the number of moles, I have the total volume, so that's going to give me a concentration. So my concentration of my fluoride ions is equal to my number of moles over my total volume in liters, which gives me a concentration of fluoride of 0.060 molar. Okay. Now let's recuperate here. Now what the heck am I doing again? I want to find the pH of the solution. Here we are. I want to find the pH of the solution. And so we figured out we're at the equivalence point. That means I have the same number of hydrogen as hydroxide. So the only thing that's going to impact my overall pH of my solution is the ions that are in solution. And so the ions in solution, the sodium isn't going to have an impact. It comes from a strong base. But fluoride, because it comes from a weak acid here, is going to give me this secondary reaction, this side reaction, which is going to produce some of this hydroxide. That means that we're anticipating that this solution is going to be slightly on the basic side. But in order to find out how much of that hydroxide we're making, I have to figure out how much fluoride I have. Okay, so we're going to take this information then, and we're going to plug it into an ice box, because we're scientists, and that's what we do. Okay, so let me do that little side reaction again. Here's my fluoride and my water. Giving me hydrofluoric acid again, which is weak, and my hydroxide, which is making my solution basic. And now I'm going to do an ice box, or an ice table, and I'm going to plug in the concentration that I just calculated from the first part for my fluoride. Now we're disregarding water in all of this because it's a pure substance, it's a pure liquid, so it's not going to be in our equilibrium constant expression. Everything is 1 to 1 to 1 to 1, so we're losing a molar concentration here. Okay, and we have none of this to start off with. Add. And again, it's not that we didn't have any of this to start off with, it's just that it all got used up in the first part, right? So now we're just focusing on what's happening with the fluoride ions. So we end up with this. Now our K expression, we have an ion here that's forming hydroxide, so it's going to be a Kb value. In past videos, we said that ions tend to not have easily accessible Kb values, but we can utilize the Ka value of the weak acid. So the Ka value for my hydrofluoric acid is actually pretty easily look-upable. So here's the literature value for my Ka. And recall, to find the Kb then, I can use this relationship. The Ka times the Kb is equal to Kw. So the equilibrium constant for the weak acid times the base gives you the equilibrium constant for water. So if we use that relationship, then our Kb value is equal to 1.5 times 10 to the negative 11th. Whoops. That's an oops. So that 10 to the negative 11th here is equal to x times x all over my reactants. Now the nice thing about the difference between this concentration and this Kb value is there's a big enough difference that I can disregard this x. And that's because of significant figures. When we round this thing, it's going to be such a big difference that it's still going to round to the same value. So I end up with x squared. I'm kind of flipping sides here. X squared is equal to 9.0 times 10 to the negative 13th. Okay. Now if I take the square root of both sides, then I end up with x is equal to plus or minus, and that would be 9.5 times 10 to the negative 7th. We know we can't have a negative concentration and that these x values represent physical quantities, so we're going to disregard the negative here and call this the concentration of our hydroxide is equal to 9.5 times 10 to the negative 7th molar. And now using this information, I can calculate the pOH. That's the negative log of this concentration. So the pOH is equal to 6.022. I'm going to just kind of keep sig figs here, and then we'll round at the end. So I'm playing a little bit fast and loose with that. Okay, so here's my pOH. I know that the pH plus the pOH is equal to 14, with as many sig figs as I need. In this case, I'll need 2. So when I rearrange and I solve for the pH, given this pOH value, I end up with 7.98 when I round. Phew! So if we go back to our original question then, because this is where it all started, was what is the pH of a solution at its equivalence point? So we're doing a weak acid with a strong base. So if we picture those titration curves of a weak acid, we're adding a strong base to it. So we're increasing in pH, increasing in pH. We hit the equivalence point where the hydrogen is equal to hydroxide. And that means that these guys are essentially canceling each other out, and the only impact on pH is going to be from the ions. We figured out our concentration of that fluoride. We used an ice box to figure out the impact of that on the hydroxide concentration. We calculated the pOH from that hydroxide concentration, and then that got us to the pH. Ta-da! All right, if you have questions, as always, on that, don't hesitate to drop me a line. Otherwise, I'll talk to you again soon.